So the second talk is personalized diffusions for top-end recommendation and presented by Georgios Karypis.
Good afternoon, everybody. Do you guys hear me okay? Very good, very good. So I want to talk about some work that we're doing in Minnesota last, I would say, year or so. So this is work that was primarily done by the two students, postdoc student work contact. Is Athanasios Nikolakopoulos and Dimitris Berberidis. And this is also joint work with Georgios Giannakis from the Molecular Computer Engineering Department. And the pictures are here, so you guys can know what they look like. There's a big green button in scroll. So anyway, we are day 3 of the recommended system conference, right? So we need to justify why recommended systems are important. So I'm not do that, right? But what I'm going to do is I'm going to just sort of set the stage in terms of the stage in terms of the problem that I'm interested. And the problem I'm interested in is that of the top-down recommendation. So the setting that we're working on is, we're given a set of users and some items, and a user item interaction matrix, right? And the goal is to essentially find a recommendation vector, pi v, right? That will compute a recommendation score for every item of a particular user by taking into account the items that the user has interacted with in the past, right? And all the historical information we have about the user and the items, prior interactions, okay? And the concept method that I'm using are the methods that rely on item-based models, okay? And the way those item-based models work, right? So you learn a matrix W, which is usually an item-item similarity kind of matrix, but like the type of matrices that you need the previous stuff, right? And then you use those matrices to actually derive the recommendations by essentially recommending items that are similar to the items that the user has seen in the past, okay? And mathematically, usually they express it in the form of essentially a matrix vector, okay? So these kinds of methods have been very popular, and in the best paper talk yesterday, this is some of the strongest base models we have today in terms of top-down recommended systems. Okay? However, they do have a limitation, right? And the key limitation of that is that they rely entirely on direct item-to-item relations. Okay? And that creates problems if the data set is extremely sparse, in the sense that they cannot reliably estimate similarities between pairs of items, for which cannot reliably estimate similarities. Okay? So to address this problem, there have been a lot of techniques that can be developed. One set of techniques that is of interest to the start are those techniques that rely on random walks. Okay? And essentially what they do, they treat that item-to-item similarity matrix in the form of a graph. Okay? And then they perform random walks on the graph to be able to derive the recommendations. Okay? So to put things a little bit more concretely, the way those methods work, right? So I have a graph. This is my item graph, right? So a particular user. Sorry. So for a particular user over here, I have sort of a starting probability, which is really the distribution in terms of the historical item that the user has interacted with in the past. Okay. You usually apply some sort of a random walk process, right? And either do some sort of a case step random walk over here, right? In which I go case steps on that graph, or do a personalized prediction. Okay. And I use those random walk processes to compute a landing probability, and use those landing probabilities to perform the recommendation. Okay? So that approach has been shown to be very effective in actually addressing some of the limitations of the item-based models. They're actually very good in addressing this related question. Okay? However, one of the problems with that approach is that if you look at the equations over here, you'll see that the user-specific component, right, is only that initial starting probability. Okay? This is the only thing that we subsequently review. Right? And everything else are the same for all the users. Right? So the degree to which those methods can be personalized, they depend entirely from where you start. Right? And not from there. So the purpose of this work that we're doing over here is we're trying to improve upon it. Okay? And to this end, we introduce a new stochastic process that is designed to be much more personalized than the standard random walk. So the way the process works as follows. So we have a random walker, right? and for which the random walker will have k's bias coins. Okay, in the first step, the random walker will flip the coins. With a certain probability, it makes one step into the transition matrix. Or with the probability 1 minus mu sub u comma 1, right, it goes back to k. Right? In the second step, it draws another probability. Right? And again, with the probability mu sub u comma 2, it makes a forward step. It goes back in. Right? In the third step, it does the same thing. Okay? So each step, whether or not we make a transition or not, is determined by a transition parameter that is specific to that region. So mathematically, the way you write the thing is you have a transition matrix, G of mu sub I, right, that contains both the moving forward part, as well as also the jumping back to the beginning part, right? And then landing probability for a regular user is a result of that multiplication. Okay? So you can see in the process, I start from the user-specific starting, distribution vector, right? And every step, right, I have a transition probability matrix, right, that is specific to the user and depends on that step. Okay? So the parameters of that stochastic process is personalized to each individual. Okay? Not only where you started from, right, but also every step that you take, right, is selected for this individual user. Okay? And this is really the stochastic process that we're doing. And the whole purpose of our work is, can we estimate those parameters of the process so that will lead to higher one-base values. Okay? So the learning problem is formulated as follows. So for a particular user, what we do is we sample one of the items that the user has interacted with in the past. We will call that thing as a positive item or as a target item, right? We also sample a set of negative items that the user has not interacted in the past. Right? So those tau is negative. Okay? And then we create a vector h of u that is of size the number of negatives plus 1. Right? That has 0 on the negatives and 1 on the positive one. And then we use a thing to estimate that least square problem over here, okay, in order to estimate the different parameters of those transition probabilities. Okay? And in the solution to that, right, we use a thing as those user-specific transition probabilities for each one of those things. Okay? So solving the problem is actually, it's very hard. Right? Because what you have an uncommon form for that. But it can be shown, right, that this problem, the previous problem, is equivalent to that, which is going to minimize this expression over here, in which that part of it is just a vector, right? This is a matrix that epsilon e sub u over here is just a selection matrix, and you get something to worry about that. But this is the standard least square problems, in which s of u is this matrix over here. Okay? And once I solve the least square problems, then I can use that expression over here to derive the various new parameters of interest. Okay? And the good thing about that is that constructing that S of u can be done actually very efficiently because it involves k sparse-matic vector palettes. Right? This is my initial starting probability, right? I do a sparse-matic vector palette of that. Then do another one with the result of the previous one, and so forth. Right? So I have k of the SPNB operations to construct that matrix. Right? I use that matrix to solve that problem, the standard least square problem. Okay? And then once I have solved the least square problem, so this is the forward substitution, right? In which I use a thing to the first part of the equation is mu sub u comma k. Then I apply that thing and I estimate the mu sub u comma k minus 1 and so forth. So this takes only like 40k operations to do that. And then things really run fast. Okay, so it's giving the sum. So the algorithm looks like that. So initially I construct the matrix, I solve a sleep problem to give it my initial W matrix, or item matrix. Then I create a transition probability matrix that is a scaled version of the sleep matrix, right? And And then for every user U, I solve the previous optimization problem. Okay? And that gives me the model parameter that I want for that personalized stochastic one. Okay, so we did some experiments. We used a bunch of different data sets. We used the Google 1 million, the Yahoo data sets for music. There was an Amazon data set, and this is a Netflix data set. And compared with a bunch of different methods. Our method is the last one, is the blue one, and the performance is the work of MBCG. And you can see that, across the board, it does better than the rest of the methods. Okay? In some of the data sets, the gains is significant, some of the data sets, again, probably achieved. Okay? We did compare against strong baselines, and we did better than 3, which is good. Okay? And also, we do much better than a lot of the recent, DP1 and low baselines. And the advantage of that approach is that it's actually computational efficiency. So over here I report 3 times. So this is the time required to actually build that item-to-item transition matrix by solving the CD problem. You need the other pre-processing step, right? And then this is the time that it takes to recommend per user. By recommending per user is to learn the new sub-I parameters for each user on the fly, right? And use those things to actually compute the recommendations. Okay, you can see that the time is best both for the users as well as the time per user. You can see that for most data sets, it's in the milliseconds range. Okay, so you can actually fit the model on the fly and use it in the flight state. So I think that's my last slide. So conclusions, right? So we developed the personalized diffusion method. It's able to show like an state-of-the-art recommendations. It's computationally very efficient. And then one of the things that I cannot talk about, and it's in the paper, there's an alternate way of dividing those diffusions that rely on a pre-existing dictionary, or sort of a family of predefined diffusions, right? In which you can actually start being able to interpret what those diffusions mean, right? So that the idea to actually make the models be interpretable, as opposed to being pretty much a black box. And I'll stop.
We have time for maybe one question. Over there. Would you like to stand up? Could you stand up for the student team?
Thank you for the wonderful talk. Can you elaborate on how do you compute EU on slide 7?
Oh, sure. Yeah, that would just keep it really quick. So EU, the only thing that EU is actually just a selection datasets. Let me tell you, essentially what that means. So remember how I have constructed H of U, right? H of U has essentially T negative plus 1 rows, right? So those are, the items of my data set, right? In which one of the items is positive, and we say 1,000 items are negative, right? So essentially that involves 1,001 items. So what E is essentially just a metric that will select the corresponding 1,000 plus 1 rows of that transition probability matrix. It's just essentially a row selection thing, right? So that will allow you to express the thing in terms of the square. So this is like essentially a syntactic kind of secret, just focus on the column of 1,000. Make sense?
Okay, thank you. Let's thank our speaker.